welcome everyone. So today we'll have Katie Zhao from our EC department to give us a talk on her recent work on combining application level opportunities with algorithm hardware code design for edge intelligence. So let me first briefly introduce the speaker. So Katie is an assistant professor in our EC department. She just joined us earlier this year. She obtained her PhD degree from Rice University. Her research is mostly focused on computer architecture, domain-specific accelerator chip design, and applications to AI-powered intelligence functionalities and resource-constrained edge devices. So she has received multiple awards and distinctions, including IEEE Micro's Top Picks 2023, first place demonstration, and 32nd ATM SIGDA University demonstration, and the 2023 Ralph Budd Award for the best thesis from Rice University. Katie, the floor is all yours. Thank you.
Thank you. Thanks for the invitation. So it's my pleasure to have this opportunity to introduce my work, because I know that this is a very disciplinary seminar. So my work is like to combine the application algorithm to design to the devices. So let's start. The title of my talk is Marrying Application Level Opportunities with Algorithm Hardware Code Design for Ubiquitous Edge Intelligence. AI has achieved amazing performance that record-breaking performance that exceed our previous imaging. For example, by using AI, we can generate photorealistic images and even videos for interactive communication. And of course, the ChatGPT, I believe that all of us are using it. At the same time, there is a growing demand bringing the AI-powered functionalities to our daily edge devices, like our cell phones, wearable devices, medical devices, and etc., etc. Running the AI functionalities on the edge can give us a bunch of benefits, like the enhanced privacy, which is quite important for scenarios where the data is sensitive. And also it can help us to save the communication latency and to give us a better usage of the network bandwidth. This is also very important for the applications where we, for example, the VR and AR, we need to have immediate communication with the machines. However, to really enable the ubiquitous edge intelligence is non-trivial. The underlying reason is that the powerful AI algorithms usually come with complex computation requirement and the memory storage requirement. Here are two examples. The first example is for 3D reconstruction, which is really used for AR, VR, and self-driving vehicles. In this model, we have over 100 terror operations. And the other example is the language model that the ChatGPT is based on. However, we have a look at the end devices. What's the results available here? Here is the example from latest Meta VR glasses. We can see that it only has very limited compute and storage resources. And compared to the requirements, there are two orders of magnitude smaller. So it's far behind the requirements. As a result, when we really run the powerful AI algorithms on the small edge devices, we cannot have a good performance. So there's a gap between the requirement of AI algorithms and what we have on edge devices. So I think that's the most challenging factor if we want to enable ubiquitous edge intelligence, the requirements of the powerful algorithms and the available compute and storage resources on edge devices. And when we consider the real application requirements, this gap will be even larger. For example, when we use the edge devices, we really want to have a good service, and then we need to have high performance, high throughput, and low latency. And also, the edge devices are usually battery powered. We hope to run it with high energy efficiency to reduce recharging. And even
okay. Now, okay. So although currently the edge device is small, but we want it to be smaller and smaller to give us a user-friendly and a social-friendly for small form factor. So this is the question that motivated my research. So how to enable the ubiquitous edge intelligence? How to how to really enjoy the AI-powered functionalities in our daily life. And the answer or the key insight is that through a cross-layer optimization insight, from the algorithm from applications to algorithms to architectures and even down to the hardware or circuit chip design. So in my mind, we should do algorithm hardware co-design to explore its algorithm and hardware level opportunities, and then do the real hardware implementation to really implement these advantages. And in addition, we should also think about from the application level, how to reduce the application level redundancies to really boost the performance. And through this co-optimization, cross-layer optimization, we can really unlock the potentials of ubiquitous edge intelligence. And this idea is also championed by a lot of researchers. And today I want to show a series of my work to show this insight and how can really implement this insight in our research. Let's elaborate more about this insight. So a holistic solution from the algorithm application level, algorithm level, architecture level, and down to the chip design level. So for the algorithm and the architecture level, I've explored to do the algorithm hardware co-design to explore the algorithm level opportunities to really improve the performance, including the throughput and efficiency, the algorithm accuracy. Only motivated by the promising performance through the algorithm and architecture level exploration, then we can go to the real chip design, the hardware implementation. And this time, we need to consider more things here, the area efficiency and the control efficiency, which cannot be like covered in the high level exploration. And after we have a hardware, a single chip, it's not enough. We need to demonstrate it in the real hardware system. So after that, I integrated this chip in a real hardware system, the VR/AR system. And at that time, amazingly, I found that we can explore the application level opportunities. So there are more opportunities at an even higher level to reduce the redundancy in the application pipeline, to further co-optimize all this hardware system. So through this holistic solution, we can really towards energy and latency efficient ubiquitous edge intelligence. And today I will plan to introduce 3 works that introduce the architecture and the chip and the system level work. So first, I will introduce this work called Smart Exchange in the algorithm hardware co-design concept. And after that, I implement this Smart Exchange algorithm in a real chip design. And this chip is further integrated into a VR/AR system for the eye tracking in VR/AR, and we call it the iFacCam. In this system, we only have 1 chip, but for the more intended eye tracking workloads, we can scale up the system and we have a multiple chip system to satisfy the even larger scaling out requirements, and I call it iCode. So in today's talk, I will start from the algorithm hardware co-design architecture, then to the chip design, and then to a single chip system and to the scaled up system. So first, let's go to the Smart Exchange one. Okay, so it's a Smart Exchange. Let's first see the motivation. Why do we call it a Smart Exchange? If we have more like knowledge in the hardware design, I think most of us have this knowledge that the data movement cost is much higher than the computation cost. For example, if we want to fetch a unit of data like 8-bit from DRAM, then the cost will be 200 times higher than the energy cost of 1 Mac operation. So the question is that for the AI algorithms, we have a large amount of parameters or weights. We have to use DRAM to store them. And then fetching data or the data movement between DRAM and the on-chip resources dominates the energy consumption, which can be higher than 95%. A question came to us that can we trade the higher cost memory access for the lower cost computations? In other words, can we greatly reduce the data communication between DRAM and the chip, but slightly enlarge the computations? And in this way, we can achieve a better overall performance. Of course, the answer is yes. That's why we call it Smart Exchange. We trade the higher cost memory access for lower cost computations. So how can we do it? We through this co-design. We through this algorithm hardware co-design. And in the following, I will first introduce the algorithm and then go to the real hardware accelerator design. So here is a high-level overview of Smart Exchange. Before going into the details, I want to share the underlying insight and learn from this exploration. So for the weights, there are a lot of redundancy, and in this work, we hope to find the underlying structure of the weight. And in this way, we only need to store the underlying structure instead to store all the original weights. And Smart Exchange is one example. In Smart Exchange, we decomposed it into a small basis matrix and the coefficient matrix, and only need to store the basis and coefficient matrix instead of the original weight. Let's see how can we do it. So for each weight filter, we first stack it into a single matrix and then decompose it into a very small basis matrix, which is usually 3 by 3 matrix, and the coefficient matrix. We found that in this coefficient matrix, we can enforce sparsity in this coefficient matrix. And as a result, we no longer need to store the original weights, but instead we only store the base matrix and the coefficient matrix, and use the vector multiplication to calculate the original weights when needed. And in this way, we can greatly reduce the memory capacity requirement to store the weights. And also for the non-zero elements in the coefficient matrix, we further quantize it to power of 2 formats. So in this way, we no longer need to do the multiplication operations. Instead, we can use the much lower cost shift operation when restoring the original weights. So here is a summary of the sparsity. Here, sparsity is not a scalar sparsity or unstructured sparsity. We use structured sparsity, which is more hardware friendly. Specifically, we use the vector-wise sparsity, where one row of elements in this coefficient matrix are all zeros. This is really hardware friendly because we can keep the structured sparsity even for the original weights. For example, in the convolution layer, it corresponds to the row-wise sparsity, and for the point-wise convolution layer, it corresponds to the channel-wise sparsity. Maybe you are curious that it's kind of old story for the convolution layer, and here the channel-wise sparsity is what happened for the matrix multiplication or the FC layer in transformer models. So in transformer models, if we apply this algorithm, we will also have structured sparsity where a series of 3 weights are all zeros. So this is the sparsity used in this Smart Exchange algorithm. By using it, we can directly skip unnecessary computations to boost the energy and the time efficiency. But is it enough? No, because for the existing commercial devices, it does not support the restoring operation to restore the original weights. And in addition, for the structured sparsity, the existing edge devices cannot fully utilize it. In order to fully utilize the potential of this algorithm, we further propose a dedicated accelerator architecture. And by doing so, we evaluate across a wide range of models and datasets. It can achieve 6.7 times energy efficiency improvement and over 90 times efficiency improvement.
This is improvements in inference time.
Only inference. Yes, this work on with target inference. This is published in 2020 ISCA, and for the journal paper, the TNL paper, we extended it to training, still fine tuning, not training, fine tuning. Okay, so this is the algorithm. So motivated by this algorithm and the architecture level exploration, we further go to the real chip design. So we do simulation, but always we have a question that is that true? I want to say that that's true. We really implement it in the chip design and tape it out. So at the architecture and the algorithm level, we explore the throughput and efficiency and accuracy. And when we design the chip, we need to consider more things like area and the control efficiency. So let's see what we have to deal with. So first, we hope to fully utilize the Smart Exchange algorithm to save the weight storage and excess energy, and also to run the structured sparsity to fully unleash its potential. And at this time, we also need to consider the chip control cost, which can be as high as 10% of the overall energy consumption. we have to deal with it if we really want to implement this design. And here we design a customized ASA to minimize the control overhead. Let's go through it one by one. So first, I will briefly introduce this microarchitecture of the chip. In this chip, we have computation resource. We call them PE lines. And also we have memory to store the input and output activations, the memory to store the weights. And also in this chip, we want to use it to support the smart exchange algorithm. So we have some dedicated modules to support the smart exchange algorithm. And also we have a on-chip controller with a customized ASA to reduce the control overhead. So first, say how can we really use a chip to fully utilize the smart exchange algorithm or the decomposed weight parameters. So let's recap the smart exchange algorithm. So after the smart exchange algorithm, during inference, we only need to store the basic matrix and the coefficient matrix, and then to use computations to restore the original weights. So in our chip design, we only need to store the basis matrix and coefficient matrix in DRAM and also at the high level memory hierarchy. And then we can restore the original weights at the lower memory hierarchy close to the computation sources. And between them, we introduce a U compute unit to do the reconstruction, which is to do the vector multiplication or the shift add operations to restore the original weights. Please remember that we only have power of 2 values in the quantized coefficient matrix. So we only need to do the shift and add operations here, which are very low cost. And in this circuit, we will store the basis matrix locally in this unit and then fetch the needed coefficient matrix when we need it and then restore the original weights. So that's the way we trying to minimize the storage and the access energy cost for weights. So after that, let's consider how to fully explore the structure sparsity, the vector-wise sparsity. So vector-wise sparsity, we can skip unnecessary computations. But there's no free lunch. We need to consider the overhead. The overhead is that we need a higher activation global buffer bandwidth. Let's see why is it true. For this structure sparsity, we have different weight chunks. Or for example, we have different weight channels. Or in the transformer model, we have different matrix, and the sparsity pattern are different for different parts of the weights. And in the real hardware design, we run them in parallel. So for different weights that need to be run in parallel, it will need different activations. So that means that we need a higher input bandwidth to satisfy all the different sparsities. And here is like evaluation or profiling results in to motivate this work. In our evaluation, we found that for the point-wise convolutional layer, when the sparsity ratio is higher than 50%, a smaller global buffer bandwidth cannot satisfy it, which is the same as the original like design. If we only consider a dense work, and when we come to the 3x3 convolutional layer, if the sparsity ratio is higher than 75%, then we cannot give enough bandwidth. And the 50% and the 75% sparsity ratios are the common case in our evaluation. So in order to solve this higher input bandwidth requirement, we insert a dedicated buffer. We call it a sequential write parallel read buffer. By using this buffer, we can increase the bandwidth by 2 times, but only slightly enlarge the area overhead, which is less than 1%. It's negligible. And to do so, in this buffer, we can sequentially fetch data from the high-level memory hierarchy and store it temporarily in this input buffer. And when the data is needed, we can stream them out and read them in parallel. In this way, we can increase the input bandwidth. And I also want to emphasize that this is also like a free lunch because we only need to pay less than 1% area overhead. So let's come to the control cost. In the real chip design, we need to pay attention to all the things, including the control cost. And in order to do so, we need to solve these challenges in the asset design. First, why do we have such a large amount of energy that is consumed by the ESA? Because we need to do the frequent fetch instructions from the instruction buffer, and also we need to decode these instructions very frequently. And in addition, we need some on-chip resources to store these instructions. In order to solve it, we fully utilize the features of the AI algorithm. So we can use a single instruction to control multiple hardware components and run them in parallel. In this way, we can reduce the instruction fetching and the decoding frequencies. And in addition, because the computations of this chip is quite repetitive, so we can predict them. That's a feature of the AI algorithm. So we can use one instruction to control tens and even hundreds of processing cycles. It's not very common for like a CPU or DSP algorithm. So this is a unique feature of AI algorithm. We can use one instruction to control a long time of processing frequencies. In this way, we can again save the instruction fetching and decoding. In addition, because there's a lot of repetitive operations in this algorithm, so we can greatly use the jump instructions to save the instruction buffer. Actually, this although we called it a customized ESA, it's general for AI algorithms because for all the AI algorithms, it have competitive computation patterns, and also for all the AI accelerators, we need to consider a parallel processing. So these three features of our ESA can also be extended to other AI algorithms. So that's the brief introduction of this chip design. After that, we really implement this chip in a hardware system, the eye tracking system for the eye gaze prediction in VR and AR applications. So in this way, we can further explore the application level opportunities to reduce the redundancy in the application level. Okay, before that, I will briefly talk about the requirements of eye tracking in VR AR and why it's challenging, and we need to explore the application level opportunities. So eye tracking is an essential human-machine interface modality in VR AR. We use it to predict the gazes of our eyes. By doing so, it can enable a lot of downstream functionalities like the foveated rendering. After eye tracking, we can know the zone that is gazed by the eyes, and only need to have high resolution in this zone and greatly reduce the overall computing overhead in the rendering. As pointed out by a recent work from Meta, eye tracking in next generation VR AR devices has a much higher requirements in performance. First, it needs to have over 240 FPS throughput and milliwatt power consumption. And in addition, because eye tracking, we want to really like have a social friendly AR glasses. We hope it could have an even smaller form factor. However, for the existing solutions, the eye tracking in VR AR is one order of magnitude slower and also have a large form factor due to this lens-based camera. And in our iFlyCam system, we integrate two components. The first one is a lensless camera to reduce the thickness of the eye tracking modular. This lensless camera can be 5 to 10 times thinner than the lens-based camera. And also by integrating this camera, the lensless camera, with our proposed AI accelerator, we can finally achieve these three requirements simultaneous, including the small form factor, over 240 FPS, and milliwatt power consumption. So this is I will give a very brief introduction of this lensless camera. So this lensless camera can be 5 to 10 times thinner because we can replace the lens with a binary mask and put the binary mask very close to the sensor. However, by using this binary mask, we can no longer have readable image, and we need to do matrix modification of computations to restore the readable image to enable the following eye tracking functionalities. And here is our demonstration. We demonstrate by using this is a FlyCam camera and also our AR7 chip and integrated using FPGA interconnection. And here is the measurement results. By using it, we can really track the gazes of our eyes. and then enable a lot of like downstream tasks. So in this design, as mentioned, we explore the application level opportunities. We call it a predict then focus pipeline to reduce the spatial and the temporal redundancy in the eye tracking application pipeline. And in addition, we combine it with our algorithm exploration and also our AI search chip to fully utilize the algorithm benefits and utilize the as we proposed before. So let's go to the predict then focus pipeline. Here is the baseline, what we usually do. In the eye tracking, in the eye tracking pipeline, we usually, it will directly use the input image of the eyes for gaze estimation. Okay, I think I'd better, I didn't notice it, I'd better move the bar over here so that you can see the title of each side.
No, we can see.
It's okay?
Here is okay.
Here is okay.
Yeah, here's
yeah. So let's see the opportunities of this eye tracking pipeline. We can see that first, there exists spatial redundancy. Spatial redundancy means that for each image, we only need a small portion of all the pixels. For other pixels that contain the skins of the eyes, it's useless for eye tracking. So we only need to focus on the region of interest. For other regions, they are useless. So we call it a spatial redundancy. And for a series of input eye images, we found that we only need to update the region of interest for a small part of all the input images. We call it the temporal redundancy, which means that we do not need to update the region of interest for every frame. In order to fully utilize or to reduce the spatial and the temporal redundancy in the eye tracking pipeline, we propose this predict and focus pipeline. We have two models here, one eye detection model and one gaze estimation model. So first, we use the eye detection model to extract the region of interest. And then for the following more complex gaze estimation model, it only needs to focus on the region of interest. By doing so, we can greatly reduce the number of operations or the computation overhead. In addition, in order to fully utilize the temporal redundancy, we found that we only need to run the eye detection model on 5% of all the frames. And by doing so, we can further reduce 20% of the computation cost. And we also evaluate our pipeline against an industry-led challenge. We found that we can really match the performance of the winner in this challenge, which validated the performance of our pipeline. And here is the full system setup. We fabricated this chip in a 28 nanometer technology and further establish a system with the phantom camera, this chip, and to demonstrate the performance of this system. Amazingly, we found that we can achieve all three requirements, including throughput, smaller form factor, and high energy efficiency. And this work won the best demonstration in DEC demo. So this is only one chip system. In real eye tracking application, we hope to run a more general pipeline instead of just using the eye detection model. We hope to use eye segmentation model. And then this time, we use a scaled up system to run the segmentation model. In the following, I will say why should we use this model. So in this eye code work, we run eye segmentation model because it's more general for AR and VR. It's also like recommended by Meta. And by using segmentation model, we no longer can do both gaze estimation and also the direct gaze interaction in the following applications. So eye segmentation is more general. In the previous design, we only show eye detection. But compared to eye detection, eye segmentation model give us a more challenging requirement. First, because we use eye segmentation model, the number of operations is 2 orders of magnitude higher than that in the eye detection model. And in addition, it will have a larger figure resolution. And also for the gaze estimation model, it has a larger number of operations. So the question for us is that how to design accelerator or how to design the system that can satisfy the eye segmentation model pipeline without significantly increasing the chip area and the memory bandwidth. Zhao, please.
question. So for different models, for different algorithms here, the difference is everything is implemented in transformers, right?
No, sorry, not transformer, CNN model. CNN model.
A CNN model. So the difference between the model is that the model size and
Model
the
size, yeah, and the model structure.
model structures.
Segmentation model, we use UNet, and for the segmentation model, we use like a FNet or depth-wise convolutional layer mainly.
And the model is already trained offline, so that
Offline, only
so
inference.
the implement so it's loading the model and
Yes, be more accurate. We even need to customize the model for each person.
Okay, thank you.
Thanks for the question. Okay, so we call it workload orchestration. Remember that in this pipeline we have two models, and previously we briefly run one model and run the other model. So when we consider the scenario of segmentation model and the gate estimation model, what will be the difference? Previously we use the time multiplexing mode where we run these two models once per time. We run a segmentation model or the gate estimation model. However, we found that it requires it can enable high resource reuse opportunity. It's from a hardware perspective. However, in order to run the much larger segmentation model, we have a large area budget. So the peak resource usage need to satisfy the requirement of eye segmentation, and we'll have lower resource utilization for the gaze model or the yellow model here. Another way to run these two models are using concurrent model. We run these two models concurrently. And because eye segmentation model only to run at a lower frequency, we can amortize the overhead of eye segmentation model, the blue model here. However, because it only have very little resources, the hardware reuse opportunities is quite limited. So they will have a lower energy efficiency. So how can we marry the best of both modes? We propose a new workload orchestration mode. We call it partial time multiplexing. This is because that we found when we run the gaze model or the yellow model here, the hardware utilization is not the same. We have a very high utilization for the convolutional layer, but a lower utilization for depth-wise convolutional layer. And then our proposed idea is to run the other model, the eye segmentation model, when to the unutilized PE lines, or when we run the depth-wise convolutional layer here. In this way, we can win both. We can run the gaze estimation model for the convolutional layers, which has a much higher utilization, is near 90% hardware utilization. And then for the depth-wise convolutional layer, we can insert the eye segmentation model on the underutilized PE lines to fully utilize the hardware. And in this way, we can win both. We can amortize the overhead of eye segmentation model and also that's enable a high hardware reuse opportunity for the eye segmentation model. And after this idea, we further demonstrate using multiple chips and found that we can achieve the real-time performance even for this much larger, two orders of magnitude larger segmentation model. And this work was selected as micro topics in 2023. So that's all for the work I hope to share. And looking forward, what will we see? I believe that we are facing a more exciting area for ubiquitous edge intelligence. Here's from the market perspective. Let's show the number here that with the development of more AI algorithms, or even with the ChatGPT, we hope to really enjoy the benefits of them in our daily life, and it will have a larger market to motivate us to move forward. And to move forward, what should we do? I summarize my thinking into 3 keywords: wider, deeper, and faster. Wider means that besides the traditional applications, we need to consider the more emerging applications that have been revolutionized by AI algorithms. Here I want to show an example. We call it 3D reconstruction. This new algorithm is called the NERF. There's a lot of news to motivate that NERF is so good so far. However, when we consider your hardware performance, its performance is quite limited. So let me introduce the algorithm first before going into the work we've done. So new NERF is to generate a new field or new images, giving a sparsely sampled scene imaging. For example, if we enter this room, we only need to capture several images as the left figure here. And then we can use the nerve to generate the image of this 3D scene and give arbitrary view images of this scene. So we call it a 3D reconstruction. And this new algorithm, nerve, has revolutionized this field. However, for this new algorithm, although we can use it to enable numerous applications, it's not easy to really enjoy it. Yeah, because for this nerve algorithm, we no longer need to do inference. We also need to consider the training. Training means that when we enter the brand new 3D scene, we hope to restore the 3D scene after several seconds or so. And in addition, for this algorithm, we need more data instead of like one image to do image classification or segmentation. Now we have a bunch of images and to restore the 3D scene. And in addition, this model is no longer a N model. We need to consider the real 3D scene, so it's irregular and much more complex than the N model. So in order to overcome all these challenges, we propose a serious work. So first is the work on inference to enable the real nerve inference. It's published in 2022 DEC ICCAT. And after that, we're exploring the training of nerve in 2023's paper. We call it instant nerve. And after that, this year, we finally published our work of nerve chip, which can achieve both inference and training in real time. So what we are going on, I hope to mention that it just received the best paper award in Micro 2024. It was held last month. And what we are doing now, we want to expand the application of nerve algorithm. So after 3D reconstruction, we can use the information of this 3D scene to enable a lot of downstream tasks. And now we are exploring the nerve-based SLAM systems. So it's our ongoing work. So this is one meaning of wider. Wider means a wider range of applications. So wider also means that more application metrics. So previously, we mainly focused on the throughput or the accuracy. Now we need to consider more. We need to consider the cost, the robustness, and even consider the environmental influence of when we run AI algorithms. We call it the carbon estimation. And one of our current work is to explore the carbon estimation modeling for the advanced 3D and 2.5 integrated circuits, and it's published in this year's DEC. Okay, so now let's go to the second keyword, deeper. In the previous work, we only explored the traditional CMOS technology, but we may find that for the CMOS technology, it has inherent limits. And what should we do? Is to explore new technologies, including the processing memory, the more advanced 3D and the 2.5 integration, photonics, and a lot of the emerging technologies. So we call it deeper, to go deep into the device level. And here is an example. Maybe you are curious that what can we do in LLM? One of the example here is to explore new emerging technologies to enable instant retrieval augmented generation in LLM. So the motivation is that we found that the data transfer between the storage, the SSDs, and the computing resources are the bottleneck for RAG LLM. So we use the emerging storage processing to move the RAG part into the SSD. And by doing so, we found that we can decouple the RAG part apart from the LLM backbone and hide the RAG behind this LLM backbone for most of the cases. And if we directly evaluate this RAG searching operation, we can achieve a much improved speed up. So this is the meaning of deeper, going deep into more emerging technologies. So let's go to another direction, that faster. When we're doing the real hardware design, it's really time consuming and it takes a lot of work, a lot of time and a lot of work. And it usually takes like 1 year to tape out one chip. So in order to ease the process of chip design, hardware design, and even this whole optimization process to reduce the design complexity, to reduce the time to market, and to reduce our labor and the risks, we propose several automation tools. And one of the ongoing work is to do the LLM-aided chip design. So in summary, I believe that that we are facing an even promising future of AI-powered ubiquitous edge intelligence. And to really enjoy the benefits of ubiquitous intelligence, we need to explore more wider, more emerging applications and more real-world metrics, and deeper going into the device design to explore emerging technologies. In addition, faster to use some automation tools to really automate this whole optimization process. So that's all for today's talk. Thank you all for coming, and it's really pleasure to present here and thank all my collaborators and students.
Questions for audience?
When you do that low-rank approximation type decomposition, how can you guarantee the matrix is sparse?
Sorry, I didn't get your point.
Like when you decompose the original matrix into two, and how can you guarantee each of them is sparse?
I think your words is that if we consider more metrics, like if we consider both carbon emission and the latency, how can we achieve both?
The question said at the very beginning.
Very beginning.
You have this decomposition.
Okay,
Smaller
decomposition.
matrix times
Okay.
basis matrix times the sparse parameters. The question is why the coefficients are sparse?
Why is coefficient sparse?
Yeah. So for which I guess for which application or which specific scenarios?
Yeah, because usually when you do those decomposition, not necessarily sparse, right?
Oh, okay. So first, it's not low rank decomposition. It's still full rank decomposition, and then after decomposition, it's through like we found that there is some sparsity. But we believe that the underlying reason is that the coefficient matrix does not consider too much underlying information. Instead, we can store most of the information in the basis matrix here. So the coefficient matrix, if it contains information, it's quite sparse. So that's why we can sparsify it. And from the algorithm perspective, in order to do so, we need to do the fine tuning. After decomposition, we grant the source sparsity and then quantize it and do it iteratively.
So just a follow-up question here. So do you find a special basis matrix here in order to make the coefficient sparse?
It's more like a design choice. Yeah. I think you mean for the we talked about the at that time we talked about the convolution layers on ImageNet dataset and also some convolutional models on the detection applications, and they all work. Yeah.
Right. So for these applications, what kind of basis matrix you take?
3x3 basis
Oh,
matrix.
no. What kind of basis matrix? Because you probably need to take some special basis matrix to make the coefficient sparse, right?
Okay, I got it. So it's basically we like at the very beginning have a higher sparsity ratio, and then check the accuracy and to train it. And if it cannot satisfy our requirements, then we will have a lower sparsity ratio.
Oh, I see.
Yeah,
Okay.
that's through like evaluation.
Train.
It's trained. It's trained.
I see.
Model is trained.
I see.
We cannot really know it before evaluation, but usually we can have higher than 50% sparsity. And for the layers that are close to the output, the sparsity ratio can be even as large as 90%.
Oh,
In the system, in the implementation, the matrix is fixed, right?
Oh yes.
So after you sort of offline just decide it, then everything is fixed.
Yes. I mentioned that we also try fine-tuning on-chip fine-tuning of this algorithm. So during the fine-tuning work, we kind of fix the sparsity ratio, and only like after several runs, we will move some of the non-zero elements to 0. So we also try the fine-tuning on-device fine-tuning. Yes.
And also the accuracy is fixed, right? So when you do quantization and sparsity matrix decomposition, first you fix the accuracy.
Accuracy is the optimization target.
Okay.
We kind of for several iterations, we fix the sparsity ratio, and use the accuracy as a target. Yeah.
About 3D reconstruction. I think a more conventional way is to use the LiDAR coupled with gyroscopic and accelerometer data to generate a 3D object of from multiple images. How is NERF better than that?
I think you mentioned the key points. You need to use LiDAR. And in NERF, we only need cameras, RGBD input image. This will be okay. It's much cheaper. And you can use it by using your cell phone like this. And also the accuracy can be higher than all the previous work that based on RGBD images.
Thank you.
Thanks for the question. Please.
Yeah, thank you for this talk. And I have a question for one of your last slides. And you said about trying to use LLM to automate the chip design process.
Yeah.
I'm wondering, are you mainly using LLM as proposal generators to generate like chip designs and then do some evaluations?
Here, currently we are focusing on the Verilog generation. So like coding the hardware design instead of using like the EDA tools, but using it to generate Verilog code. Or more specifically, you can see that in my work, one important hardware component is missing, the control part. So we develop a ESA for the customized accelerator, but we do need a CPU to control the accelerator. And usually this is missing for all the hardware designs. So our current focus is to automatically adjust the CPU core so that it can control different kinds of accelerators. This is our focus. And if you have a look at the recent work in the EDA conference like the DEC, there are a lot of works in Verilog generation. So currently, I think most of the work is still focused on the code generation. It's similar to the programming code generation, but I believe that the design to synthesize and even layout is ongoing. Yeah.
I see, but just LLM can generate code, but in your case, it might be generate some specific code to the hardware.
Yes, the control part, the CPU control part.
Okay, and another question is like it's also about the NERF one. So when you said it's an edge GPU, I'm just really intrigued to know like what kind of GPU you are talking about, like when you are trying to do NERF and also SLAM applications. Is it still a desktop grade GPU or is actually like a JSON Nano?
JSON Nano, or JSON Nano, or a little bigger than that, or the JSON ONX, a little bigger than Nano. Like this part.
Oh, I see.
Of course, we don't want to run it on desktop.
So basically it's already possible that we can use a JSON kind of GPU to do like real-time NERF and SLAM.
Not real-time NERF. It's kind of 10 FPS or 20 FPS, but usually for the NERF application, we hope it can run the inference at 60 FPS.
Thank you.
That's my question.
So I have a high-level, very curious question. So, it seems like what the community is doing is that, most of the time the machine learning researchers come up with a new architecture, and then we try to optimize the hardware to follow, right? To optimize the running time performance. What about the other direction? How much we can do in the other direction? That means when we come up with all of them, so we already think about hardware design, because when you say code design, I really think that, the two sides will work together, right? But if you look at the major architectures, most of the time it's machine learning guys you mentioned them without thinking about hardware at all. I mean, they may be very, very suboptimal, right, in terms of hardware thing, and also nobody says that's the best architecture available, right? If they do a little bit fine tuning or just slightly change things, actually the performance will be comparable. So how much we can do in that direction?
That's a really good question. In our work, we hope to combine both algorithm and architecture level opportunities. But I believe that for the expertise in algorithm, they may find that it's a little hard or there's a gap between what they have to train the model. And in the community, I found that there's a lot of work that compose the hardware dataset or hardware augmented dataset for the training. For example, one of our work is a hardware NAS bench. We provide or we mirrored the hardware, the performance of the components in the bench dataset and provide its latency and throughput performance. In this way, you can like embed the hardware metrics in the training process. I think there's some like existing or ongoing effort in this direction to provide some dataset with the hardware features and even some community to really do the algorithm hardware co-design. I think it's really like encouraged at least in the DEC or ISCA conferences. And also, if we have looked at the algorithm papers, I found that more and more people are trying to embed the hardware metrics as one of the optimization target. I think that's very good. And for our like more hardware person's perspective, we should provide the data set so that you can directly use it. Yeah, that's my thinking.
Just to follow up with the answers there. So how much do you think is possible to actually abstract out the hardware layer? Because what's happening here is that typical machine learning researchers, they don't know hardware well. And they are just blindly play with the math and play with code. So if we can really make this automatic, right? Like abstract out the hardware thing. Again, I don't know how much we can do that because this remind me about in programming, we know that C tends to be very efficient, but you need to dig into the very low level thing, and Python tends to be much less efficient, right? But recent years, people use this kind of just-in-time compilation, this kind of technology to really speed up Python, and sometimes it can even almost catch up with C, in efficiency. So hardware side, is it possible to do a similar thing like? I don't know what form it will take because I don't know very little about hardware, but
that's really like a promising direction. I believe a lot of people are working on it. And also I have this question that if I want to do the hardware design, I also need to know a lot of things in the algorithm level.
Yeah.
It's kind of it's hard and even very challenging. But the good thing that I think algorithm people are more open. They will open their code and there are a lot of libraries available. But for hardware, we kind of close the community, maybe because we need more resources and more time. But now there's some open community for even hardware, the chip design community.
I see.
If we can have the open source code and some open source designs, then we can surely embed this into the whole system optimization. Yeah.
Thank you.
Thanks. Great. Any other questions? No, let's thank the speaker again. Thank you.